Hello everyone, I'm Karthik Mohan Muralidharan. I'm a software engineer with about 8 years of experience in full stack development, specializing in Salesforce. I've also worked with BigQueries in Google Cloud Platform and Python for data analytics. My expertise lies in designing and developing user interface solutions and enterprise integrations to deliver exceptional user experiences. I've seen firsthand how the UI can make or break a user's experience and efficiency, especially in complex enterprise systems. That's why I'm so passionate about the topic we're diving into today, emotional intelligence in the crowd. In this presentation, we'll be exploring how we can create adaptive interfaces that don't just process data, but also actually understand and respond to the user's cognitive and emotional state. We'll start by looking at the current implementation gap in this technology and then highlight the proven benefits that emotionally aware interfaces offer. We'll dive into the methodologies and accuracy of how these systems infer user states non-invasively and discuss the various adaptive mechanisms they can employ. We'll also review the significant performance improvements observed. We will also discuss some time on the ethical considerations and user acceptance factors, which are essential. Finally, we'll touch upon the implementation architecture, a roadmap for adoption, and future directions in this exciting field. My goal is to show how this is a leap forward in making our enterprise software more intuitive, supportive, and ultimately more human centric, particularly when the stakes are high. Let's dive into it. The core idea is to transform our enterprise software by embedding effective computing principles. This means we need to create systems that can detect and intelligently respond to our cognitive and emotional states in real time. While the benefits like better decision quality and user satisfaction are well documented, the actual implementation of these emotionally aware systems in the enterprise environments has been limited. We will explore the architecture and methodologies behind building these responsive interfaces that adapt dynamically by analyzing non-invasive interaction data, which is particularly crucial for enhancing performance in high stakes scenarios. Okay, so let's look at the current implementation gap. As we can see from the charts, and as research confirms, there is a striking disparity. Despite clear evidence of their effectiveness, enterprise systems are significantly behind consumer applications when it comes to adopting these effective computing principles. To put some numbers on it, only about 18% of the current enterprise systems utilize any effective principles. Some studies even place the figure for comprehensive emotional awareness lower, around 13.6%. Compare that to the consumer space, where nearly 69% of applications already feature adaptive elements. What's particularly concerning is that this gap is even wider in high stakes environments where you'd expect the benefits to be the most sought after. We see adoption rates as low as 7.2% in the financial platforms, 5.8% in the healthcare management systems, and a mere 3.4% in the critical infrastructure operations. Now, given that the technological foundation has matured considerably, we can suggest that the primary hurdles are now more organizational than purely technical. Okay, let's move on. Let's see some benefits. Although we are seeing a lot of gap, in the implementation of these adaptive systems or these computing principles. The proven benefits of these interfaces are undeniable and quite compelling. For example, in a high stakes field like healthcare, studies have found that professionals using emotionally responsive interfaces experienced a 27% reduction in diagnostic errors and a 34% improvement in their decision confidence scores, particularly during the critical care situations. That's like a direct impact on patient outcomes and clinician assurance. Across various complex enterprise environments, integrating effective computing has been shown to reduce cognitive load by 37.2%. Imagine how much that can alleviate mental fatigue and improve focus. Consequently, we also see a 29% increase in task accuracy across multiple sectors. And these are not just isolated findings, there are comprehensive studies. For example, there is one involving about 1,800 participants that has established statistically significant correlations between like the interface adaptability and enhanced performance metrics. These improvements clearly demonstrate the transformative potential we're talking about, especially in demanding enterprise settings. Let's go to the next slide. So, how do these systems actually infer our emotional or cognitive state? It's done through very intelligent and pretty clever, effective inference methodologies, focusing mainly on non invasive data. For example, let's go first with the interaction velocity analysis. This looks at things like typing rhythm. Variations here can correlate quite strongly with cognitive load. Like there are some values here, which is statistically significant. For example, if your keyboard interaction speed drops by 21.7%, it's a consistent indicator of increased cognitive demands. Other method is error pattern recognition. The way we make mistakes can be very telling. Clustering patterns of errors, for example, can predict fatigue with around 72.8% accuracy. If someone's correction behavior suddenly jumps by 28.5%, it often signals frustration. Even the types of errors, like increase in navigation errors versus data entry errors, can create recognizable emotional signatures. Then there's this workflow sequencing behavior. When we are cognitively overloaded, we tend to deviate more from optimal task paths by as much as 52.7%. Machine learning models can analyze these sequence patterns alone and detect decision hesitation with about 74.6% accuracy. Let's go next slide. Okay, let's dig a bit deeper into these non-invasive detection methods because they rely on the subtle cues from our everyday interactions. We've touched on the typing rhythm variations, like these correlate with cognitive load at an R value of 0.73, like a 21.7% drop in the keyboard speed. That is a strong signal of increased mental demand. Also, we have the mouse movement patterns. They are pretty insightful. How you move your mouse can show correlations with states of emotional discomfort or uncertainty, essentially creating recognizable digital signatures of the user's experience. Then we have a temporal engagement metrics. This includes things like dwell time. So, if a user's dwell time on a particularly complex interface element increases by 38.4%, it correlates strongly with the state of confusion. Similarly, if their attention switching frequency, that is like how often they jump between elements, increases by around 57.3%, it's a reliable indicator of information overload. All these indicators are then processed by increasingly sophisticated models and using supervised learning, particularly ensemble based architectures, we are now achieving around 79.5% classification accuracy across five distinct emotional states. Okay. So, what is the accuracy of the effective inference methods? Right? Now, let's consolidate the accuracy. As you can see in this table, the numbers are quite promising. For like the overall emotional state detection, we are looking at around 77.4% accuracy. The typing rhythm correlation with cognitive load is a strong 0.73. Mouse movement patterns show a correlation of 0.68 with emotional states. We can predict fatigue from error patterns with about 72.8% accuracy. Decision hesitation detection from workflow sequencing is at 74.6%. And the correlation between dwell time and confusion is a high 0.77. Importantly, when classifying across these five distinct emotional states, our accuracy is now reaching 79.5%. What's really pushing these advancements is the underlying technology. Cloud based processing infrastructures have slashed inference latency, that is, the time it takes to make a detection, by nearly 62% just since the year 2020. Furthermore, learning approaches are enabling privacy preserving insights across organizations while maintaining a remarkable 88.3% accuracy, which you'd get from a centralized model. This is key for scaling these systems effectively and ethically. Okay. Okay. So the systems infer a user state, but what happens after that? This is where the adaptive interface mechanisms kick in, allowing the interface to respond intelligently. First, information density modulation. The system, what it does is the system can dynamically adjust the complexity of the interface based on the cognitive state. Let's say, for example, reducing interface complexity during detective cognitive overload. This has resulted in a 32.6% decrease in decision errors and a 35.8% improvement in task completion times. Contextual assistant deployment. Let's say if confusion is detected, the system can proactively offer help. This has been shown to reduce the support ticket submissions by a significant 38.2% and decrease the task abandonment rates by 26.4%. Workflow simplification. Okay. During like high stress periods, the interface can restructure complex tasks. This has led to a 31.5% reduction in error rates and a nearly 25% decrease in reported stress levels. Interface contrast enhancement. The system can make dynamic visual adjustments based on attention state. Visual tracking studies confirmed a 37.6% improvement in attention allocation to critical elements with such dynamic adjustments. And crucially, intelligent timing of interventions. This optimizes notification delivery to reduce interruptions, leading to a 41.7% reduction in workflow interruptions and a 27.3% decrease in task recovery time. These mechanisms work together to create truly responsive environments. Modern implementations are achieving around 71.8% accuracy in state detection with an impressive 89.2% user satisfaction rate regarding the appropriateness of these adaptations. Okay, so performance improvements. Now let's consolidate these performance improvements because they truly highlight the impact of emotionally aware interfaces. As we have seen from various studies, in healthcare, we are observing a 27% reduction in diagnostic errors and a 34% improvement in decision confidence scores. When it comes to task efficiency, users are completing tasks 35.8% faster, and there's a 29.4% increase in overall task accuracy. So it's not just faster, but it's also more accurate. The cognitive benefits are substantial, with a 37.2% reduction in measured cognitive load and a 32.6% decrease in decision errors. And these systems even reduce the burden of support needs, leading to a 38.2% reduction in support ticket submissions and a 26.4% decrease in task abandonment rates. These figures collectively demonstrate the significant positive impact across a range of critical metrics, especially in those high stakes enterprise environments where decision quality is absolutely paramount. Now, what is the implementation architecture that powers these adaptive systems? So, it can generally be broken down into four key layers. The first one is data collection. This involves gathering those non invasive interaction patterns we've discussed: typing behavior, mouse movements, workflow navigation, and so on. And then we have the next layer as the inference engine. Here we have our machine learning models that process this interaction data to detect the user's emotional and cognitive states. And then we have the next layer, which is the adaptation rules. This is the decision logic. Based on the inferred state, these rules determine the most appropriate interface modifications. And then there's the interface adaptation. So, this is the dynamic adjustment the user actually experiences, like changes to the information density, contextual help popping up, simplified workflows, or visual enhancements. The key factor here is speed. Modern implementations like a four-layer framework documented by Morales can achieve an inference to adaptation latency of just 285 milliseconds. This allows for truly real-time responsiveness, and it's a cloud-based processing that provides the backbone, enabling these sophisticated models while maintaining performance across diverse enterprise environments. Now, we absolutely must address the crucial ethical considerations. This technology is powerful, and with that power comes responsibility. First, transparent consent. It's not enough for systems to be smart. Users must understand and agree to how their data is being used. Properly implemented transparency measures can increase user acceptance by a 67.3% compared to opaque systems. When it comes to sharing interaction data, a striking 78.4% of users are willing if they are given granular opt in permissions versus only 29.2% who accept blanket consent models. This really highlights the need for user control. Next, inference accuracy and fallbacks. So, no system is perfect. Graceful degradation protocols. What happens when the system has low confidence in its inference? That's what graceful degradation protocols are. This can reduce negative user experience by nearly 64%. Implementing confidence thresholds, where the system defaults to a static interface if unsure, improves overall user satisfaction by almost 39%. And a major ongoing challenge is the algorithmic bias mitigation. So, unmitigated systems can show inference accuracy by as much as 24.8% across different cultural backgrounds and 29.3% across age groups. This is clearly unacceptable. The good news is that by using a balanced training data set and a cultural calibration, these disparities can be significantly reduced, down to around 8.3% and 10.6% respectively. Okay, let's continue with the user concerns and safeguards. The primary concern is employee monitoring boundaries. It's understandable that users worry about how effective data might be used. In fact, 71.5% of the surveyed enterprise users are concerned about its potential misuse for performance and evaluations. That's a right concern. However, implementing technical safeguards that explicitly prevent the extraction of individual performance metrics from this data can boost the system trust ratings by nearly 60%. It's about support, not surveillance. We don't want to micromanage people. User override capabilities are also absolutely essential. Users need to feel in control. Systems that provide easy to use override mechanisms achieve a remarkable 82.3% higher user satisfaction score than those without such controls, maintaining user agency over their experience. This all points to the importance of an ethics by design approach, building ethical guardrails into the system from the very beginning and being transparent about them doesn't just address privacy concerns, it substantially increases system adoption. Longitudinal studies have even documented a 53.2% higher implementation success rate for systems that incorporate ethics by design principles from the outset rather than treating ethics as an afterthought or a mere compliance checkbox. So, what are the key user acceptance factors that drive adoption of these emotionally aware interfaces? The data is quite clear, as illustrated here, and backed by numerous studies. First and foremost, acceptance is heavily influenced by the implementation of these ethical safeguards and transparency measures we've just discussed. Users need to trust the system and understand how it operates. Secondly, providing granular control and clear, accessible override mechanisms significantly boosts their willingness to adopt and use these systems. It's about empowering the user. And thirdly, specifically addressing those concerns about the misuse of data for performance evaluation through robust technical safeguards is absolutely essential for building and maintaining trust, especially within enterprise environments. Ultimately, users are more likely to embrace these technologies if they feel respected, in control, and confident that the system is there to support them, not to judge or undermine them. Okay, so implementation roadmap. Bringing these sophisticated systems to life requires a structured implementation roadmap. It begins with assessment and planning. This involves thoroughly evaluating current interfaces, identifying those high stakes workflows where adaptation can yield the most benefits, and crucially establishing solid ethical frameworks and clear consent models from day one. We also need to determine the most appropriate adaptation mechanisms for specific use cases during this phase. Next is pilot implementation. The strategy here is to deploy in limited controlled environments, ensuring robust feedback mechanisms are in place. Transparent communication about the system's capabilities and its limitations is vital, as it's as is the comprehensive user training, especially on how to use any override controls. Following the pilot, we move to refinement and expansion. This is where we meticulously analyze pilot data to improve inference accuracy and ensure the adaptations are genuinely appropriate and helpful. Any identified bias issues or other user concerns must be rigorously addressed before gradually expanding the system to additional workflows and user groups. Finally, continuous improvement is an ongoing commitment. This means establishing persistent monitoring of system performance and user satisfaction, regularly updating the underlying models, to enhance accuracy and potentially expanding emotional state detection capabilities, and always maintaining open channels for user feedback. Okay, so as we look to the future direction and draw our conclusions, the cloud interface, the cloud infrastructure evolution is a key enabler. Continued improvements in processing efficiency and the maturation of federated learning approaches will continue to reduce the technical barriers to implementing these sophisticated systems. This also paves the way for cross organizational insights, where privacy preserving federated learning allows for shared learning and model improvement, maintaining around 88.3% of centralized model accuracy without compromising sensitive data. The ongoing ethical framework development is paramount. We need standardized approaches to transparency, consent, and bias mitigation to ensure these technologies are properly implemented responsibly and can scale effectively. Let's not forget the profound potential for enhancing occupational well being. Beyond pure performance gains, these systems can significantly contribute to reduced stress and improved workplace satisfaction for the users. What we are witnessing is a significant evolution in enterprise software design philosophy. It's a shift from a singular focus on functional efficiency to creating systems that dynamically and intelligently respond to human cognitive and emotional needs. As the technical hurdles continue to diminish, our most critical work will lie in thoughtful considerations of these design principles and the unwavering commitment to robust ethical frameworks. This is how we'll create systems that don't just perform tasks, but genuinely enhance human capability and respect fundamental rights and privacy. Thank you for giving me this opportunity to speak to you on this paper. Have a good day.